Hi and welcome to this segment where we are going to talk about correlation and regression. In particular, for this segment we shall focus on regression, and at the end of the segment we should be able to have covered the first objective here. These are the objectives, okay? And the objectives which we want to cover for this segment here is how to calculate and interpret a simple linear regression equation for a given set of data. And then in the next segment we shall move to correlation, where we shall look at how to calculate and interpret simple correlation. I think coefficient, okay, simple correlation coefficient, okay, between two variables, and then how to determine whether the correlation is significant or not. So straight away we get to describe what regression is. Regression, in this case, in here we refer to the estimation of parameters in a linear equation, okay, that can be used to predict values of one variable based on another. So our goal here is how can we estimate parameters which can be used in a linear equation, okay, which can be used in a linear equation for purposes of predicting one value based on the other. Okay, simple in this case, simple in this case means we are only referring to two variables. Okay, we are looking at the relationship between only two variables. Of course, you can, in the real world, it is not as simple as this, that it is just two variables, one is depending on the other. No, you can have one which is, dependent of multiple factors. For instance, maybe the number of road accidents is dependent on many factors, which can include maybe mechanical condition of the vehicles, the roads, how they are constructed, what else, the drivers, the weather, and so many other things. Okay, so those are just some of the examples that come to my mind immediately here. But in this case, since we are looking at this for the first time, I presume for the first time we shall just look at the simple one, which is for two variables, although there exists those where you can look at more than two variables, okay, and this is under what we call multiple regression. Okay, and the linear in this case here refers to the relationship which can be estimated by a straight line. Hope we all remember the equation of a straight line, which is given by y is equals to mx plus c. Okay, we are going to use here something which is similar to this. So I mentioned something to do with depending, and that one variable is depending on the other. So in this case, when we have two variables, or even more than two, there will be one variable which will be dependent. Okay, we usually denote this by the y. That is the one which will be on the vertical axis here. This is the dependent variable, and then the independent variable will appear here on the x-axis. Okay, so the dependent variable is one whose values, okay, we want to predict or to forecast. For instance, y could be the number of road accidents, okay, and then x could be any factor any factor upon which y will depend. Maybe we can say that the number of road accidents can depend on maybe we can check the weather. Okay, then we can see how does the weather contribute to the number of the road accidents in this case. Okay, so this will be the independent variable, and then this is the dependent variable. So the dependent variable is that whose value we want to predict stroke or forecast, i.e. we want to forecast or predict the number of equations based on given data, in this case which is the weather conditions. It can be something else. And then the independent variable, okay, I don't know what more to explain to this, except that it is what explains the dependent variable. Okay, so down here we have we talked about that when we are talking about linear, okay, this linear regression, we are simply looking at relationship which can be expressed in the form of a straight line. So we have a straight line here, and this is the equation format of a straight line. Y is equals to mx plus c. So in here we have already said this is the dependent variable, and then this is the independent variable, and then this is what we have, our constant, and then this one here is the slope. Okay, and the beta one here is the what? Is the slope of this line here. So the slope here equals to beta 1. This is the constant or the intercept, beta naught. This is the constant, or in this case the intercept, and this is the independent, and then this is the dependent. Okay, we shall keep it simple in such a case. So this is how we would have this relationship here. We would simply say y is equals to beta naught plus beta 1 x1. Okay, how can I, okay, let's see if we can simply use, if we said that y1 is a parameter, I don't know how what measurement one would use in case this were describing the weather condition and so on. I don't know, you can, that is a different story. So if this were to affect, I mean if this would be the relationship, okay, then intuitively beta naught would be the number of road accidents when x naught is 0. Okay, in absence of okay, if this factor is not considered, okay, if that is 0, if that factor is not considered, then this would be the number of road accidents. Perhaps for this equation it may be hard to explain, but you know, when we look at very many other numerous examples, then we can try to intuitively get the idea of what this beta naught here is going to explain. But in a vague way here, I can explain and then say that beta naught would be the number of road accidents that would happen regardless, you know, regardless of the weather conditions. Okay, let's say when okay, when this x is 0, when, now if I say when this x is 0, I don't know how to explain it, when the weather conditions are what, absent, but then what would that mean? Not a nice example, but I hope you try to get what I'm trying to explain here intuitively. And then the slope here would, this beta 1 here would explain how much, okay, y is going to change due to a change in x here. For instance, if x increases by just 1 unit, okay, then we would expect y to increase by a factor of beta 1. Okay, when x increases by 1, then y here would increase by a factor of beta 1. And please note that we are talking about this independent variable, an increase and causing an increase here, and that is because the slope here is positive. Okay, it is a positive slope. If the slope was a negative, then it will be a different story. They will be inversely related. So when one factor here increases, then the other here would do what? Would decrease by, you know, that given factor, and so on. And okay, however, in real life, this is not as straightforward as this. So what happens in real life is that The relationship is just usually average in a sense that we can have maybe this set of data points here, okay, perhaps which we are describing here, the weather pattern. Again, maybe it's a valid example, however it's proving quite hard to explain in here. So what can we use? Maybe income. Okay, maybe someone says if this is income, okay, and this is expenditure. Okay, income and maybe expenditure. You are looking at various people in the society, you look at their income, and then you want to see whether it is related to the expenditure, whether the income here levels can explain the expenditure patterns. So usually it's not going to be as straightforward as that all data points are going to lie along that straight line and everything is nice and uniform. No, it's usually that you can find this family has this, and then you try to collect your data and then plot, and then you find out that you have something which looks of this sort here. Okay, so when it looks like this, what we have to do is simply we have to fit a line. Okay, we fit a line, okay, which tries to minimize the distance between all these points here. For instance, we can call the distance between, okay, we fit a line in this data here such that these epsilons here, okay, i.e. the distance of these points, of each of these points from the fitted line, is at its minimum. Okay, that is what we try to do here. The idea of linear regression is to draw a line that minimizes these errors here, the epsilon. So that is why, okay, instead of having our our equation just written as y is equals to b naught plus beta 1x, we are going to add this error term here. Okay, we add this error term here to take into consideration these errors, that this line here is simply fitted, and then we have these errors here which we are trying to keep at a minimum. Okay, yeah, so that is the idea. Then maybe one thing I should look up is that patterns of regression. Is it called patterns? Like you can find, okay, when you look at a regression, the relationship, okay, okay, let me see. What do I want to look for here? Let me see. Just go to the browser here, and then linear regression. Let me see, linear regression. Curves. I don't know. Examples. Okay, let me see. Is it examples or let me see, patterns, okay, sorry, I hope okay, I think this is what images for linear regression and what. Okay, yeah, I think this is, I'll try to explain based on this. Okay, so maybe these are really small. Okay, no, let me see, linear regression, patterns of variation. Let's look at this one here. What do they say? Okay, it's not okay. The pattern of variation is called, if I don't find it in the next 1 minute, I am simply going to, how do you summarize a linear regression? Let me see. Let's see. think I should have done this before. I should have prepared this before we started here. Detailed view towards data science. Let us just look at this. Okay. For the purposes of time, I will just try to explain this very easy. So in this linear regression here, you can have okay, let me leave that for now. I think I'll explain it in the next video here when we are talking about correlation. I think it is more related to the correlation when I'm trying to look at the relationship, whether it is strongly positive, strongly negative, or there's no relationship at all, and so on and so on. So let us just end this video with what I wanted to look at here. We have an example of how to fit data here, and then we come up with an equation here in this case. So if I can go back to the browser here, I try to search somewhere, and then I found some data points here. Let me see here some data. It was about groundwater survey here, the groundwater survey, and then in the following they give us some data here which I downloaded and then I saved. And where we had a column which the first column, the X, which had the pH of the well water, and then the Y where we had the bicarbonate, and that is parts per million of well water. I think this is the concentration of the bicarbonate in here. So like I said, I was smart enough for that one, so I already downloaded it and I imported it into the MATLAB workspace here. I hope you remember last time we did, did we do MATLAB? I'm not sure. I think with this class we did something to do with Python, but I think for this one here, I think let us just do with the MATLAB here. But I've already introduced you to the MATLAB, I suppose, so you should be well familiar with some of these. So this is the workspace here. I saved it in here, the sample. So what we are going to do is that we are going to use what we call a scatter diagram here. So a scatter diagram, we can use it. I'll just write it out for you and then we see. So first, of course, now we have our data here, but then we first have to extract it. So we are going to say that X is going to be equal to the sample here, okay? And then I want to extract the first column. So we are going to say that that will imply that I want values in all the rows and in the first column, okay? So I'll suppress the output here because I don't want it to, it will just come and fill up the screen. Maybe just to be sure, we can maybe just try to extract the first value here of that column vector, and it should give us the value here, which is 7.6, just to be sure that we did the right thing. Okay, that's okay, 7.6. That's fine. So next, then the Y, no prizes for guessing what we are going to do. The Y is simply going to be all rows and in the second column, okay? Oh, what did I do? Sorry, I did Y again. So I have to go back and reset the X to that, okay? And then just to be sure, again we can do that, okay? Then I would like to clear the screen here, okay? So this is supposed to be Y, okay? And then yes. So next, just to be sure, we want to make sure that we have 157 here as the first value in that column, just to be sure, okay? Again, I will clear the screen. Please note the difference between CLC, which simply clears the screen, and do not use this. When you use this command here, clear, it will clear all the variables which you have saved here in the workspace, okay? So I won't press that. So the next I said, oh, we want the scatter here, and then the command is the scatter and then XY. So we press enter here, Okay, and this is our scatter diagram or our scatter plot here. So this is our data here. So if we want to fit our linear equation here, I think we go to tools. Yeah, we go to tools, then we go to basic fitting, then we choose linear here. Okay, yes, so this is our linear plot here. Okay, so if I also want to show the equation, okay, I can click here, show equation, and then I close. So this is it. Maybe if we also want to maybe insert labels, so in the X label here, we said it was, I think they said it was the pH of the water. Was it the pH of the water? I'm not so sure. Let us see our data here again. So what was it saying? X is the pH of the well water, okay, and then Y is the bicarbonate parts per million. So we have here pH of the well water. Okay, that's okay. And then we come back here, and then the Y label, we said it is in parts per million. Okay, great. So now we have an equation here. So the linear equation here, which is describing this relationship, is y equals to negative 38 x plus 4.3 times 10 to the power 2. So I want us to make some sense out of this. Okay, I've written it somewhere here. Okay, so we have said that in our example there, we found out that we used our MATLAB here, and then we found this to be negative 38 x plus 4.3 times 10 to the power 2. Okay, so this is our intercept, and then this is our slope. You can see we have negative slope here. Okay, and yes, and then now here, remember y is the parts. What was y? Y is the parts per million. Parts per million of the bicarbonate. Okay, bicarbonate. I'm not so sure. Is that the carbonate? Oh, I've forgotten my symbols here. If I wrote it badly, please pardon me. I don't think I remember my chemistry that well. So this is negative 38 times x was the pH, and then plus 4.3 times 10 to the power 2. Okay, so here this tells us that when the pH increases, okay, by a certain unit of measurement, I'm not a chemist here, so I don't know how they're measuring this, then we expect the concentration here in parts per million of the bicarbonate to reduce by this 38, okay, by 38 units according to whatever measurement they have made here. So after collecting the data, we know that, you know, the pH will affect the concentration of this carbonate in this particular way, you know, the inverse relationship and so on. So yeah, that is for now. I hope you have enjoyed the class, and then see you in the next class, where we shall talk about correlation. Okay, thank you, and see you next time.